This is Ray's magnetic switching generator. Parts of it I'll go through. My whole inquiry of magnets has been to find over unity results. This is my drive motor, considered my input. It has a 3/4 by 1 by 2 inch neomagnet in the middle. This back here is my flapper. It's a secondary magnet. It is responding to the rotary motion of the main magnet. I have it connected to some gearing and then to a small DC motor which works as a generator. The output or the load, I have two little flashlights. They have 9 LEDs in each one. It's not firing to maximum brightness, but it gives you the idea. I'm set at 2 volts. The power supply is not sensitive enough to get the amperage on there, so I set here a meter here. It fluctuates between around 6 and 12, something like that, so I'm calling it 10 milliamp draw at an average at 2 volts. So I want to record that. So if I have 2 volts, I have 10 milliamp. That gives me about, if you work it out, about 20 milliwatt. So it's not much. So I just want to document that there. So it's about 20 milliwatts running. Okay. So what we want to start off with here is documenting the forces for the OU event, which I think that's happening, but it does need more testing. So the object of the video is possible OU event. I'm going to show the ratio of the force in against the force out. All motors and generator efficiencies fall in the range of 30 to 80%. None commercial show more out than in. It's usually the reverse. You don't get as much out as you put in. Ray's north-south magnetic switching generator is still in development. More accurate measurements need done and improvements. This is an overall first testing. Okay, we're going to go ahead and stop it, and then we're going to have a force instrument to see what the forces are, input and output. So this is considered my input, and the flapper magnet back here is considered my output. Okay, we're going to have input and output forces measurements. I have a force measurement instrument here. On the right side is the ounces. I'm going to see how much force it takes to spin this around. That'll be considered my input. Okay. Coming around there. You see it just doesn't budge. A little bit. I finally called it a ½ ounce. Have to have something. And you'll hear it flap. Okay, I went the whole way through. So I'm going to call that half ounce. That's your input. In force 0.5 ounce. Okay, now we're going to go to the output forces, and that'll be my little flapper, my secondary magnet here. That's the one that produces the power. So, okay, so let's see what the force measurements on that would be. Ooh, these are neomagnets. This one here that I'm working with is a 1/4 inch thick. It's a 1/2 inch wide and 1 inch long. And I put another little button magnet on there just to give a little bit more power. Okay, here we are, our force measurements. And I'll start pushing down on it. There's 12. You can see that it hasn't moved off the bottom yet. There's 16, that's a pound. That's still on the bottom. And let's see where it goes here. There it went. Somewhere around 20. Finally flipped. Yeah. So somewhere around 18, 20 in there, that range. If I could get that one more time there. And start pushing down. And you'll hear it flip when I get up there now. Okay? Twenty. 22. Oh. Try that one more time. I didn't have it set. Okay, there we go. Sit there. Start pushing it down. About halfway. Not quite. 14. There it went. Around 14. Right there. And 12. We better say 12 on that. We'll go. Yeah. About 12. So we have about 12 ounces out. That's the force that is inputting into the generator, that small little generator. Okay? Okay, we'll be back in a little bit and we'll do some more testing. Okay, just for fun, I'm going to put a button battery to run it, just to show that it doesn't take much energy. I'm going to put a couple little magnets on each side of the button battery. Okay. That holds the clips on, and it's running real well. That's these little button batteries. 3-volt button battery, just kind of fun. So there's not much resistance to the turning. We'll get into that in just a little bit, okay? Back in just a second. Okay, I'm going to go into the operation of Ray's north-south magnet switching generator. The subject is switching through this north-south magnetic barrier. If you've ever worked with magnets, you may have come across this. There exists a resistance, I call it Rn for resistance in, and a resistance R out that impedes the free movement of metal or magnets in the transfer between these two fields. So I'm going to go ahead and illustrate this. I have another setup here. This is the magnet, north and south. But the barrier in between is what always puzzled me, and I couldn't get through that very easily. You can see how the magnet, it's hard to pull through here. If you can see it like this. See, an awful pull to it. But coming through that barrier, it snaps through. You have to push it through. You can see kind of how it's bending through. Really a force. So that kind of cancels out all your over unity possible gains. If you could get from this north face, these are powerful magnets. Be very careful with them. They can pinch fingers, which I've done a few times. So here again, this is what impedes that field transfer. It just can't get through it very easily. But if you put a what I call a side metal cap here, that makes a well, I'll read it here. A side cap magnet with appropriate metal shields and allows a very low resistive transfer between the north and south. Okay, and we'll show you that. Okay, and here's your north and south. See the difference? That's a neutral zone. That's all neutralization by the metal capping on the side of the magnet. Not the face, but the sides. This allows the transfer between the north and south faces. That opens up a whole new ball game, believe me. Okay, I'll be back in just a little bit. Okay, so this is one of the main components of principles behind the action of this design. This is allowing the secondary flapper magnet to easily go and pass from the north to the south. The other principle is involved, just as important, is the right angle magnetics. I've covered that in other videos, but just to bring it up, two magnets held at right angles to each other will experience a particular force either up or down in respect to each other. You can see how it flips up. You can do that with a magnet at home. Put your north there and put another little magnet coming in perpendicular right angles, and you'll feel that force either up or down. That's what's happening with my flapper magnet. It is taking advantage of the right angle magnetics, and it's enough to turn the wheels, the little gearing, turns the small generator, lights the lights. So there you have it. That's all it is. It needs more testing and so forth. If there's enough interest, I'm thinking that next video, as I do some improvements and so forth, I can make some design or the designs of it and put down and make that available for you. But anyhow, this is what it is, and it's called Ray's Magnetic Switching Generator, because the output switching little flapper, it is able to transfer and go through that north-south barrier with much more ease, allowing an output that's greater, as we tested, than the input. But this is just kind of a ballpark thing that I'm doing. There's more accurate ways, you know, the distances and this and that. But it was very promising to me. So if you have any questions, I'll try to answer those in the next video. I appreciate you watching. Make every day count. Thank you very much.